Let's start with this idea of the three-phase model, the graph of energy versus temperature. And formally, this is energy added or removed. Because we don't really care how much energy something has, we care about how much energy it's gaining or losing. The change in energy is generally what's important. And if you've got just some object that is, let's say it has a certain amount of energy and a certain amount of temperature, and let's say you add energy to it. If you add energy to the object, what would you usually expect to happen?
Goes to the right.
Yeah. Adding energy means moving to the right on the graph. But also, assuming there's no phase change involved yet, you add energy, and what else would you expect to change here? What else is going to happen?
Temperature increase.
Yeah. Usually, if you add energy to an object, you would expect the temperature to go up if nothing else is changing. So that means we're going to the right and up. So the usual diagonal line we see on the temperature versus energy graph, the three-phase model, represents adding energy to cause the temperature to rise. But that only works up to a certain point. Once you reach a certain temperature, when you get to the melting point of the solid, what happens when you add more energy? Yeah, that line's going to go horizontal as we go through that change in phase. And that horizontal line represents that we're adding more energy. We're still going to the right on the graph, but the temperature doesn't change, right? It's changing the bond energy instead. So adding more energy to change the temperature is called a change in thermal energy. Adding energy to cause a change in phase is considered a change in bond energy. And during that phase change, the temperature doesn't change. We're adding energy to break the bonds apart. We're adding energy to make the particles more free to move around, changing from solid to liquid or later on from liquid to gas. But there's no temperature change during that process. So for instance, for water, you raise ice up to 0 degrees Celsius, you add more energy, you're melting the ice, turning it into liquid water, it's still at 0 degrees Celsius. Once you've added enough energy to fully melt it, so once it's 100% liquid, you add more energy and it starts to raise temperature again. So we go back to a diagonal. And where you are on this horizontal basically corresponds to how much solid versus how much liquid. All solid, all liquid, and then proportionally in between. So for instance, exactly halfway between would be half and half. More towards the left side would be mostly solid, but a little bit liquid. Mostly to the right would be mostly liquid, but a little bit solid. Any questions on that graph so far? Yeah, go ahead.
How do you calculate if it says like, put the percentage of liquid or gas in the mixed phase?
During that mixed phase portion, how far along the bar you are graphically should be proportional to what percent is in each phase. For instance, if the substance is, let's say, 90% solid and 10% liquid, that's mostly solid, so it should be mostly close to the solid side, mostly to the left side. But since it's 10% melted, you're going to be 10% of the way along this bar. So 10% of the way towards the right side is going to be 10% melted. 10% of it is liquid. Those should be proportional.
So we cannot really calculate it, right?
You can if you have the numbers. Like if you know how much energy it would take to melt the whole thing, the amount of energy to melt 10% of it would be 10% of that amount of energy.
Okay, that makes sense. Thank you.
Mm-hmm. And the important thing there really is that mathematically, the unifying idea there is that it's proportional. That the energy required, the change in energy, and we call this bond energy because it has to do with breaking and forming bonds amongst the molecules, is proportional to the amount of mass that changes phase. So we would write this as delta N. The amount of mass that changes phase. So you could interpret that as how much of the ice melts and turns into liquid water, or on the next phase change, how much of the liquid boils and turns into gas, which may well be all of it, or might be part of it. But the important thing is knowing how much of it in kilograms changes phase. Have you seen this proportionality symbol before? So what does that mean mathematically? What does it mean when we say that two quantities are proportional to each other?
As one increases, another increases at the same time.
Yeah, and specifically at the same ratio as each other. Like let's say it takes a certain amount of energy to melt 1 kilogram. If we want to melt 3 kilograms, that's 3 times as much mass, so it'll take 3 times as much energy. If you wanted to melt 50 times as much mass, it would take 50 times as much energy, and so on. These are changing in the same ratio. If one of them doubles, then the other one also doubles. If one of them gets divided by 7, the other one gets divided by 7 as well. We can also write this as an equation. In general, if two quantities are proportional to each other, let's say if we know that y is proportional to x, that tells us they change in the same ratio as each other. But we can also write this as an equation. Not exactly that y equals x. Proportional doesn't mean they're exactly the same value. But we can say that y equals some constant times x. This is a very convenient way of writing a proportionality as an equation. Anytime you know two quantities are proportional, you can always write that as one of them equals a constant times the other one. Or alternatively, if you divide both sides by x, you get y over x equals a constant. And in fact, this might be thought of as a better definition of proportionality. If we say two quantities are proportional, we're saying their ratio is always the same value as itself, always the same ratio. So no matter how x and y change, they're changing to still be the same fraction, the same ratio with respect to each other. And this is very convenient because anytime we know two quantities are proportional, either just through experimentation or observation, if we know physically that these quantities should be proportional, like if we run experiments and find that, yes, melting 3 times as much of the ice does take 3 times as much energy, we can always write that as an equation. We can now write this as one of those quantities equals some constant times the other. There should exist some constant that we can multiply by the amount of mass we're melting to figure out how much energy it takes to make that happen. And what do we call that constant? Have you seen that in class yet? This constant, it has different names in different textbooks. Sometimes it's called the latent heat. Latent heat. Latent in the sense of sort of a hidden potential, a hidden capability. The latent heat basically means the amount of extra heat or extra energy, I should say, that's sort of hidden in an object because of its phase. Like if you've got liquid at 0 degrees versus solid at 0 degrees, they're the same temperature, but the liquid has more energy. That extra energy that the liquid has is the latent heat that we're talking about. The extra energy it has because it's in a higher phase. Or sometimes it's called the heat of melting or boiling, if we're talking about the vaporization. So heat of melting or heat of boiling or heat of vaporization, depending on what type of phase change we're talking about. It's also sometimes called the enthalpy. Not energy, but enthalpy of melting or enthalpy of vaporization. And enthalpy is a quantity we're going to get into later, but in this context, it basically means how much heat is required to make it happen. And we're generally going to write that as delta H. And that delta H here isn't so much a change in the traditional sense. You're not going to calculate this delta H by subtracting something. Instead, delta H is a property of the material. For instance, ice melting and turning into water. There's a certain delta H associated with that. Or iron being melted into molten iron. There's another delta H associated with that. Or liquid water boiling and turning into steam. There's another delta H associated with that. And the great thing about this is that it's a standardized value for each material and each phase change. So you can just look that up on a data table. If you are dealing with, let's say, solid water melting, if you want to melt 5 kilograms of ice, you can look up delta H for ice melting on a data table, multiply by 5 kilograms if you want to melt the whole thing, and that'll tell you how much energy it takes to melt all of it. Or alternatively, if you don't know delta H, well, maybe you're dealing with some new mystery material, you could try in a laboratory setting, add a certain amount of energy, measure how much of it melts, and then you can just divide to calculate delta H. So this is measurable in a laboratory setting. It's just that delta H for any typical substance that is well known, you could just look up on a data table. Any questions on that so far?
How can we access the data table?
There might be one available on Canvas. Have they sent one out to you at this point? It's going to look something like this. If that looks at all familiar, should be like a list of different materials and then a list of their properties. Have you seen anything like that yet? I
don't think so.
Okay, I think I have one on mathandcheese.org. If you go to mathandcheese.org/P7A, there's a, I don't know if I have it as a separate document, but on one of the worksheets.
You can find one on our reading for the chapter.
Okay, yeah, there should be one included on one of the documents they gave you on Canvas. So take a look in those and you should be able to find a table of values. Or alternatively, for any standard material, they can be looked up online as well. But the idea is once you have that value for a given material, you can multiply by any amount of mass you want to figure out how much energy it would take to make that amount of mass change phase. And also, anytime we're introducing a new constant like this, introducing this new concept called delta H, there are some very useful mathematical tools you can use to get more information out of that. One thing you can do, in general, anytime you've got an algebraic equation, what can you do to get more information about one of the variables in it? Like if you want to know what delta H means, algebraically, what would you do with it?
Divide by delta M.
Yeah, we can literally solve for delta H by just dividing by delta M. So this heat of melting or enthalpy of melting, I'm going to say heat of phase change, because it could be from melting or boiling. Delta H, or latent heat in some textbooks, is delta E divided by delta N. Delta H is a ratio, much in the same way that if two quantities are proportional, their ratio should be a constant value. The delta H is defined as this ratio of how much energy you're adding divided by how much mass changes phase as a result. So you can calculate that in a laboratory setting, as I said. If you measure the amount of energy and measure how much mass melts or boils, divide those, and that is the delta H for that substance. Also, anytime we're defining something as a ratio, a very useful way to think about that, we're dividing by delta M. What's the easiest number to divide by?
1.
Yeah, if we just assume the denominator is 1, if you imagine standardizing this to exactly 1 kilogram of mass, delta E divided by 1 is just delta E. So delta H, the latent heat, really is just the amount of energy it takes to change the phase of exactly 1 kilogram. And this is a very convenient way of thinking about any quantity that's defined as a ratio. Just imagine the denominator is 1, and that gives you an idea of what this quantity means. This quantity means, in this case, the amount of energy required, the cost of changing the phase of exactly 1 kilogram. Also, anytime you're introducing a new quantity like this, it's a good idea to investigate the units of measurement, just so you know what sort of quantity you're talking about, what you're measuring it in. For instance, energy. Have you seen what units are used for energy yet?
Kilojoule?
Yeah, kilojoules or joules, either way. I'm just going to say joules for now. So joules abbreviated as a capital J. And then mass would usually be measured in what?
Gram?
Yeah, grams or kilograms. And as a standard, we're usually going to use kilograms. So delta H could be measured in joules per kilogram, or often kilojoules per kilogram. And the reason for that is because if you measure it in joules per kilogram, for most substances, this tends to be a very large number if you measure it in joules per kilogram. So typically we write it in kilojoules per kilogram instead to get a smaller, more manageable number. But keep in mind, kilo just means times 1,000. So kilojoule just means 1,000 joules. But these are typically going to be listed in the data table in kilojoules per kilogram. Any questions on that so far? So as a quick example, let's say we are trying to melt 5 kilograms of ice. And we want to know how much energy that's going to take. How much heat is needed. Heat in this case representing a transfer of energy. So energy is talking about how much the substance has. Heat is talking about how much is being transferred. Heat represents a transfer of energy. So in this context, we're never going to say that an object has a certain amount of heat. Heat isn't something the object has. Heat is the process of transferring energy to or from the object. In this case, heat is going to be usually written as Q. Is the change in energy. If all we're doing is melting it, that's just a change in bond energy. We're basically going from all solid to all liquid. So on the three-phase model, our process would look like this. We're going from all solid to all liquid, meaning we're just changing the bond energy. And we can use our delta M times delta H formula. What would we write in for delta M here?
5 kilogram.
Yeah, we're melting all of it, so the delta M will just be all 5 kilograms. And you can think of this delta as a change. Delta, you usually write delta as final minus initial. So final amount of mass minus initial amount of mass. But we got to be careful here because we really have two masses we're dealing with. We're dealing with the amount of solid, which is decreasing. We go from 5 kilograms of solid to no solid at all. And also the mass of the liquid. We start with no liquid and we end with 5 kilograms of liquid. But the way this works is the masses we're talking about here should be treated as mass of the higher energy state. So for instance, if we're talking about a transition between solid and liquid, which one of those is higher energy, the solid or the liquid?
Liquid.
Liquid.
We can see on the graph that the liquid is higher energy than the solid. And also you have to add energy to change a solid to a liquid anyway. So the liquid is going to be higher energy. That means in this delta, we should be treating this as the final amount of liquid minus the initial amount of liquid. M final minus M initial of the liquid. Now, how much liquid are we assuming we end with here? If we're melting a block of ice, at the end of the process, how much liquid do we have?
5 kilogram.
Yeah, we end with 5 kilograms of liquid. And how much liquid did we start with?
0.
So our final minus initial is 5 minus 0, which is positive 5. So that's really where this number comes from. We're taking the final amount of liquid minus the initial amount of liquid because liquid is the higher energy state in this transition. If we were going the other way, if we were freezing the water, we'd start with 5 kilograms of liquid and end with no liquid because it all freezes. So if we're freezing, we'd have 0 minus 5, and that would be negative 5 kilograms. This would result in a negative amount of heat. And what do you suppose a negative number for heat represents? If heat is negative, what do you think that would mean?
Heat is going out.
Yeah, heat is going out. Heat is leaving the system, which makes sense. You've got to remove heat from the liquid in order to freeze it, whereas you've got to add heat to the solid in order to melt it. So for melting the 5 kilograms of ice, we've got positive 5 kilograms, representing that transition from solid to liquid, times delta H, which again, we can just look up on this data table. So I'm going to look for water, and it lists a heat of melting and a heat of vaporization. We want to use the heat of melting because we're talking about melting. It does list 2 values though. I don't know if you can see this, but it lists a 335 and a 6.01. And these data tables tend to list 2 values with different units, kilojoules per kilogram and kilojoules per mole. Which one of those should we be using? Kilojoules per kilogram or kilojoules per mole?
Kilojoules per kilogram.
Yeah, because that matches up with the units we already have. So I'll fill in the 333.5, which is a number you're probably going to be seeing quite a lot, kilojoules per kilogram. That way kilograms and kilograms cancel out and you're left with kilojoules. The kilojoules per mole you would use if you were instead of kilograms you were given a number of moles. If you're told the number of moles of the substance instead of the amount of mass. So that's another sort of delta H, the molar heat of vaporization or molar heat of phase change. Instead of amount of energy per kilogram, it's amount of energy per mole. Usually written as a lowercase n. So that's just another way of describing how much of the substance there is. You can talk about how much mass there is or how many moles there are. Just 2 different ways of describing the amount. In this case, though, we are talking about kilograms. So use the kilograms or kilojoules per kilogram measurement. That way kilojoule or kilograms cancels out. And we're left with 5 times 333.5. Which is 1,667.5 kilojoules. So that's just the amount of energy it takes to melt all 5 kilograms of ice. Any questions on that so far?
Hi, I have a question.
Yeah, go ahead.
I do have to leave a little bit early, but could you re-explain the kind of like final minus initial and like in terms of like the type of problem that's either like melting or freezing or?
Yeah, delta anything can always be written as final minus initial if we're talking about the passage of time. But it's important to consider what you're actually subtracting, what quantity is changing. And if you're talking about a phase change, what I was saying is there's really 2 masses to consider. There's the mass, in this case, you're going from solid to liquid. So there's the mass of solid and there's the mass of liquid. If you start, for instance, in this case, we started with 5 kilograms of solid. Time passes and we end with 5 kilograms of liquid. So when we're calculating delta M, we're certainly not going to subtract 5 minus 5 because we don't want to say there's no change. Instead, what we want to look at is how much liquid we started with and how much liquid we ended with. And we're specifically using liquid instead of solid because liquid is the higher energy state. And typically for these delta M's, we are going to be talking about the higher energy state. We started with 5 kilograms of solid, but how much liquid did we have at the beginning?
We had no liquid.
Yeah, no liquid at all. So 0 kilograms of liquid. So when we're calculating delta mass of the liquid, specifically using liquid because liquid is the higher energy state here, final minus initial is going to be, we ended with 5 kilograms of liquid, so final is 5 kilograms. We started with 0 kilograms of liquid. So 5 kilograms minus 0 kilograms.
Okay, so just overall, we would just use the one with the higher energy state.
Yeah. So if you're talking about a transition between solid and liquid, use mass of the liquid, regardless of which direction it's going.
Okay.
And likewise, if you're talking about a transition between liquid and gas, gas is the higher energy state, so you'd use mass of the gas as the indicator there.
Okay, cool.
Any other questions on that so far?
Sorry, what was that?
Any other questions on that so far? Okay.
Okay.
So
Casey, I do have to leave a little bit early, but
okay.
I'll see you next week. Thank you.
Sounds good. You're welcome. So let's take a look at thermal energy as well, because we've covered this idea of a phase change and the change in bond energy associated with that. Thermal energy is going to be somewhat different because we're talking about a change in temperature instead of a change in the phase. So if instead we're looking at, let's say, this transition here, maybe you're adding energy to raise the temperature of a gas. What type of energy would we call that?
Thermal.
Yeah, if we're adding energy to change the temperature, the energy associated with that temperature change is thermal energy, written as ETH. And since we're talking about a change in temperature, presumably this change in energy is proportional to the change in temperature. If you're changing temperature by a certain amount, that costs a certain amount of energy. If you want to change temperature by 10 times that much, it's going to cost 10 times as much energy. And because of the way we're defining proportionality, we can write this as an equation. Delta E thermal should equal some constant times the change in temperature. And we call that constant the heat capacity, usually written as a capital C. So the heat capacity is this constant of proportionality that you multiply by the temperature change to figure out how much energy it costs to make that temperature change happen. And this is a property of the object. If you have some object, let's say you've got a certain block of iron or a certain cup of water or something, that object has a certain value for heat capacity. And as before, we want to get more information about that by solving for it. Solve for heat capacity, and what do you get?
Delta E thermal divided by delta T.
Yeah, all we need to do there is divide by the delta temperature. So the heat capacity is for some object is defined as this ratio of how much energy you add or remove divided by how much the temperature of the object changes as a result. And as before, we can also get more information by looking at the units of measurement. Delta E thermal is going to be measured in joules or perhaps more likely kilojoules. And then temperature change is going to be measured in kelvins. Kelvins or sometimes degrees Celsius. But the thing is, if you're talking about a change in temperature, kelvins and Celsius are the same thing. They have different starting points, different values of zero, or different meanings of zero. But the change in temperature, it doesn't matter if it's Celsius or Kelvin as long as you're consistent about it. So heat capacity is going to be measured in joules per Kelvin or kilojoules per Kelvin. In other words, how much energy it takes per Kelvin of temperature change. And again, it's convenient to think of this as a unit rate of change. If you imagine the denominator being exactly 1, the heat capacity literally means the amount of energy it takes to change the temperature by exactly 1 Kelvin. Like if we say the heat capacity of some object is 30 kilojoules per Kelvin, this literally means it costs 30 kilojoules of energy to raise the temperature by 1 Kelvin. Any questions on that heat capacity so far? And what properties of the object do you think would determine its heat capacity? Like what, if you think of this as like a level of difficulty, like larger heat capacity means it takes more energy to get the same temperature change. What properties of an object are going to determine how difficult it is to change the temperature?
Would it be bond energy?
The bond energy is is that related? Bond energy is more about a phase change, right?
Okay.
In this case, we're not talking about a phase change. We're talking about how difficult it is to change the temperature.
Mm-hmm.
So if you just got like some object, what properties of that object do you think are going to determine how difficult it is to raise the temperature by 1 Kelvin?
Like metal, non-metal?
Yeah, what sort of material it's made of is going to make a difference. But material is not the only aspect. If you just got, let's say you've got 2 blocks of identical material, 2 blocks of iron, let's say. Are any 2 blocks of iron going to be the same level of difficulty to heat up?
So would mass also be a factor?
Yeah, the mass is going to make a big difference here. If you've got like a 1 kilogram block of iron and a 10 kilogram block of iron, the larger block of iron is going to be more difficult to raise the temperature of simply because there's more of it. So the heat capacity depends on both the amount of the substance and the material it's made of. In fact, we can set up another proportionality here. We can say that the heat capacity, capital C, is proportional to the mass of the object. Twice as massive, assuming it's the same material, twice as massive means twice as difficult to raise the temperature. That also means we can write this as an equation. Heat capacity of the object equals its mass times some constant. And that constant is called the specific heat capacity, or specific heat, written as a lowercase c. And the formal old-fashioned name for that was the mass-specific heat capacity. Because if you look at this as a ratio, the mass-specific heat capacity, little c, is just the ratio of capital C divided by the mass. It's the heat capacity per kilogram. It's the heat capacity standardized to exactly 1 kilogram. For instance, if you've got a bunch of pieces of iron that are all different sizes, they're all going to have different heat capacities. But if you standardize it to exactly 1 kilogram, the heat capacity, or the mass-specific heat capacity, little c, is the heat capacity of exactly 1 kilogram of the substance. So when we call this the mass-specific heat capacity, we just mean we're standardizing this to 1 unit of mass, 1 kilogram. And over time, this has kind of gotten shortened to just specific heat. It's an abbreviation for mass-specific heat capacity because it is the heat capacity specific to exactly 1 unit of mass. It's the heat capacity of 1 kilogram, but it's often abbreviated to just specific heat. And note that this is a property of the material it's made of. The heat capacity of the object depends on the mass and this property of the material it's made of. So heat capacity includes material and size. Specific heat is just material. So we might talk about the heat capacity of 1 kilogram of iron, or the heat capacity of 5 kilograms of iron, the heat capacity of half a kilogram of iron. But we talk about the specific heat of just iron. And the nice thing about that is since it's standardized to just 1 kilogram of the material, you can look that up on a data table. Specific heat of iron can be found on a data table. Specific heat of liquid water can be found on a data table, and so on. So typically, if you want to know the heat capacity of an object, you could measure how much heat you add and how much the temperature changes and calculate it that way. Or you could look up the specific heat of the material on a data table and then multiply by how massive the object is. And that'll tell you the heat capacity of that object, which includes material and size. Any questions on that so far? And then if we combine these together, using this description of heat capacity, we can write out perhaps a more useful formula for delta E thermal. Replacing heat capacity, capital C, with mass times little c, specific heat, we get mass times specific heat of the material times change in temperature. So this becomes a much more practical formula that we can actually use. If you want to know, for instance, how much energy it takes to heat up 3 kilograms of iron by 5 degrees Celsius, you just plug in the amount of iron here, look up the specific heat of iron on a data table, plug in how much you want the temperature to change here, multiply those together, and that tells you how much heat it costs to make that happen. Any questions on that so far?
Okay, so like the specific heat is something that we have to look up on a data table?
Yes.
Okay.
Either that, or if you, in a laboratory setting, you could measure how much energy you're adding, measure how much the temperature changes, and measure the mass using a scale, and then calculate specific heat from that. So it's certainly possible to find specific heat in reverse, as long as you can measure all the other things. And in fact, that's how we get these standardized values of specific heat for the data table in the first place. But any typical standard material that is already known, you can just look up the specific heat on the data table. Any other questions on that so far? All right, then let's try bringing this all together as an example. Let's say you have 3 kilograms of hot solid iron, originally at a temperature of, let's say, 600 Kelvin. Well, let's say 600 degrees Celsius. I think that'll make it easier to work with. So temperature 600 degrees Celsius for this iron, and as much 0 degrees ice as you want. How much ice is needed to cool the iron to 0 degrees? So we want to cool the iron all the way down to 0 degrees. And we want to make sure, ideally, we want to be using just barely enough ice. We don't want to use more ice than we need. So if that's what we're doing here, we want to figure out what's changing, what types of energy are changing. And it's useful at the start of this to draw out an energy a 3-phase model for each type of substance. We've got iron and we've got ice. So I would start by drawing out a 3-phase model graph for each one of those. For the ice and for the iron. And I usually start by just quickly drawing out as a dotted line or something, the whole 3-phase model. Just a rough sketch. And then fill in a more solid line what's actually changing. For instance, for the ice, what type of transition is the ice going through? Where does the ice start? Where does the ice end? What do we know about the starting situation of the ice? It starts
in... It starts at 0 Kelvin.
Yeah, starts at 0 degrees Celsius, which should be the melting point of ice. And it starts, that's the horizontal bar, the phase change. Would you expect it to start on the left side or right side?
The left side?
Yeah, the left side is the lower energy side, the solid side. And presumably when you put the ice in contact with the hot iron, what's going to happen to it?
Heat up.
Yeah, it's going to heat up. Wait, is it going to heat up? It's currently ice at 0 degrees. If you add energy to ice at 0, it can't get hotter yet. What's it going to do instead?
Increase in bond energy.
Yeah, if you're currently at this point on the graph, if you add energy, you're not heating, you're not raising the temperature, you're just going straight to the right. You're changing your bond energy because you're going through a phase change. So we're talking about the ice going through a phase change, just going straight to the right. And where would you expect the ice to end up here? If our options are maybe the ice completely melts, or maybe the ice doesn't completely melt, or maybe it completely melts and starts to heat up beyond that, which of those options do you think is actually going to happen here?
It'll for sure melt to a liquid.
Yeah, it's going to melt. The thing is, if our options are, also, what do we want the iron to do? What do we want to happen to the iron?
We want it to cool?
We want it to cool down to what final temperature?
0 Celsius. Same as
yeah. We want the iron to cool down to 0. So let's do this with the iron also. The iron is solid, starts off as hot solid. We want it to cool down. In fact, let me redraw the iron graph. The iron is solid the whole time, so we don't really need the whole graph for iron. There's going to be some melting point way up here, but we're not anywhere near the melting point of iron. We're going from 600 to 0. So the iron is going from solid at 600 to solid at 0. And that entire transition, since all we're changing is thermal energy, so all we're changing is temperature, that means this whole thing is just a change in thermal energy. Delta E thermal for the iron. If we want the iron to end up at 0, we should expect the ice to also end up at 0, which means the ice is going to melt, but it's not going to warm up. If we allow the ice to warm up to, let's say, 5 degrees Celsius, that means the iron has only gone down to 5 degrees and not all the way to 0. If we want the iron to end up at 0, the ice is also going to end up at 0. So our options are the ice completely melts or the ice only partially melts. The thing is, if the ice only partially melts, that means we were inefficient. That means we didn't really need that much ice. If you add a bunch of ice and you find that the ice partly melts, all the ice that didn't melt wasn't really necessary. So let's assume that we add just barely enough ice and it all melts. So let's assume that we've done this perfectly and the ice completely melts, but no further. So we've used just barely the right amount. That's our change in bond energy for the ice. And we don't need any change in thermal energy in this case because the ice has not changed temperature. That means the only things going on are a change in bond energy for the ice and a change in thermal energy for the iron. What should we assume about those two changes? If these items are only interacting with each other, if the only thing we're doing is causing the ice and iron to interact with each other, what should we assume about the change in total energy of the system?
That it's proportional with each other?
Sorry, what was that?
That they're proportional with each other?
It's not only proportionality, it's actually stronger than that. the idea is that they have to add up to 0. The total change in energy in a closed system, closed in the sense that the ice and the iron are only interacting with each other. We're not adding heat from somewhere else. We're not removing heat from the system. These aren't interacting with anything else like the air around it. We're assuming we're taking the iron and the ice, putting them together, putting them in an insulated container so no heat can enter or leave, and just allowing them to interact with each other. In that situation, we would call this a closed system, and we'd say the change in total energy is 0 because no energy can enter or leave. Expanding that out, the total energy is going to be both of these energies added together. And of course, there may be more than 2 types of energy involved. Like if we had allowed the ice to change temperature as well, we'd have a delta E bond and a delta E thermal for the ice. But in this case, we have just a delta E bond for the ice and a delta E thermal for the iron. At this point, we could fill in formulas for each one of these. Delta E bond for the ice is delta M for the ice times delta H for ice melting. Delta E thermal, we can use MC delta T as we saw earlier. So the mass of iron, in this case, 3 kilograms, times the specific heat of iron, which you can look up on a data table, times the delta temperature of iron, which is going to be final minus initial. And those have to add up to 0. Now we know the mass of the iron, we know the specific heat of iron, or we can look that up on a data table. Delta temperature is just going to be final minus initial. You can look up delta H for ice melting on a data table. So the only unknown left is delta M, how much ice melts. So if you solve for delta M, that'll tell you how much ice you need in order to make this happen. Any questions on that? So try this out yourself to get some practice. Look up these values on a data table, specifically delta H and C iron. Solve this algebraically for delta M ice, and that should tell you how much ice is needed to make this iron cool off. And that's about all the time we have for today. So have a good weekend, and I will see you next time. You're welcome.